In this lecture, we are going to see the transition probability for constant perturbation, and also we are going to see the Fermi Golden Rule. Let us say the system is under constant perturbation. That is, we are perturbing the system at time t equal to 0 up to time tau, t equal to tau. We have seen in our previous class Ck of 1 is 1 which is a function of t is equal to 1 over I h cross h prime sub km integral over 0 to tau e power I omega km tt. Now mk, that is transition probability moving from m state to kth state, is given by, here I like to highlight one important point. Most of the author uses this symbol, that is arrow is reversed, that is it indicates the bra vector and this is a get vector, but I am following this initial to final. Normally they will mention as final to initial. This is initial verb. Whatever may be, only the convention of sign, that's all. So probability m to k of t is equal to modulus square of this one. So if you take modulus square, 1 over I h cross modulus square, this matrix element modulus square, and this integral modulus square. So if you integrate this between 0 to tau, this, if you integrate this exponential term, you will get e power I omega km t divided by omega km. Of course, you have to apply this limit. 0 to tau, that limit is. So, if you take modulus 1 over h cross square, you will get 1 over h cross square. Then this modulus square, and this will be, first you substitute the upper limit. Upper limit is t equal to tau. Lower limit is t equal to 0. That means is minus 1. So modulus e power I k m tau minus 1 divided by omega km modulus square. Now we will try to simplify this. And now we got this expression. Let us find the value of modulus square of e power I omega km tau minus 1. So since it's a modulus square, you can take complex conjugate of it. You multiply, the meaning of this is multiply the complex conjugate on this function. So if you take complex conjugate of this, e power, this plus will become minus e power minus I omega km minus 1 e power plus I omega km tau minus 1. So now you multiply this e power, this exponential term first. So this will be e power 0, which is equal to 1. Then multiply this and minus 1. So minus e power this one. And minus 1 this. So minus e power plus I omega km tau, and minus 1 into minus 1 you will get plus. What about this second term, two terms, second and third term? So e power minus I theta minus e power plus I theta is equal to 2 cos theta. So this is 2 cos theta, 1 plus 1, you will get 2. So I am taking 2 outside. So this will become 1 minus cos omega tau. So 1 minus cos omega tau is equal to, that is 1 minus cos theta is equal to sine square theta, 2 sine square theta, 2 sine square theta by 2. So applying that relation, I am writing this. So here already you have one 2. 2 into 2 will become 4. 4 times sine squared omega tau pi 2. So this is the value for the numerator. And the denominator as usual, omega km square. So I am rewriting this, that is 4 times this 4 comes from this value. 4 times sine squared omega km tau by 2, and h cross squared this omega km square. Now I am bringing this 4 to the numerator, in the denominator of the denominator. That is, this can be brought as this can be brought here as 2 whole squared. I am taking omega km divided by 2 whole squared. 2 squared is 4, so 4 will go to numerator. So I am just rewriting this. Then we will see what will happen to this. So now we have seen the probability of moving the particle from mth state to kth state is this one. This modulus h prime km squared divided by h cross squared and this sine term. Uh, when tau tends to infinite, uh, delta y is equal to sine squared y tau divided by pi tau y squared. Here y is equal to omega km, omega sub km tau divided by 2. So this is y squared here, y squared I am taking. This is y. So now you need pi and tau in the denominator. So I am multiplying and dividing by pi and tau. Now this is maybe I will erase this. This is delta y. Delta y, here y I have taken as omega km pi 2. So y is equal to omega km. That also I have to remember. Omega km pi 2 is y. So this will be delta omega km by 2. Omega km by 2. You have pi tau. Pi tau I have taken at this. If you want to write this in terms of energy, omega km by definition is equal to, we have seen omega km is equal to ek minus em, that is difference between initial energy and final energy divided by h cross. So I am replacing this omega km as ek minus em over h cross. Already there is 2 here, so 2. So from delta function property, this can be written as ek minus em multiplied by 2h cross is a delta function property. So 2h cross will come outside and it is in the numerator. So you can write, you have 2h cross, already one h cross is squared is here, so it will get cancelled with this h cross, and you will get 2 pi tau, or I can make it clear that uh, I will make it clear that this can be written as 2h cross delta ek minus em from the delta function property. So now this h cross and h cross squared will get cancelled. This will become simply h cross, and there is 2 pi tau. 2 pi tau divided by h cross, then this matrix element, that is modulus square of h prime km and delta ek minus em. Now we have seen that the transition probability in moving the particle from mth state to kth state is this one. Here, first I will take sine omega km tau over 2. When omega km is close to 0, then this will be sine theta equal to theta. If theta tends to 0, theta is very small. So if omega km is very small, then we can approximate it as omega km tau divided by 2. Then what about the sine squared omega km tau by 2? You square it. Omega km squared tau squared divided by 4. Now what about this term? You divide by this term. There is another omega km divided by 2. If you divide this by omega km square, here also omega km square. So this will get cancelled. You will get tau squared by 4. That is the maximum value. So this is approximated as a delta function. So you will get maximum peak when omega close to WKM close to 0. So when this is WKM, x-axis is WKM. When it close to 0, you will get maximum peak. When it is far away from this, and one more thing is, remember that here in the denominator you have 2. So you will get 0 only if argument of this is 2 pi. This will, multiple of pi. So this will happen only when omega km equal to 2 pi 2 pi or 4 pi, even number of pi, 6 pi. Because if you take odd number pi, 3 pi, 5 pi, then you will get pi by 2. Sine pi by 2 is 1. But it will go to 0 only if integer pi. So that means it is even number of pi. So 2 pi tau, it is 0, and another 2 pi tau is 4 by tau, and 6 pi tau, 8 pi tau, both positive axis and negative axis. You know, by definition, omega km is equal to pi by tau, 2 pi tau. So this is angular frequency. 1 over tau is a frequency. So this is angular frequency, omega km. Then you can see the peak drastically reduces when omega increases. When omega increases, when tau is decreased. So when tau is decreased, tau squared will be still less. So this peak will reduce drastically. We will analyze this graph in detail now. Now you can analyze this graph. The height and width of the main peak is centered around omega km equal to 0 at 0. And as I said, decays rapidly. The omega km moves away from 0. So, and height is proportional to tau squared, and width is 1 over tau squared. 1 over tau. So this height is proportional to tau squared, you can see here. And width is here you have higher width, here low width is proportional to 1 over tau. Hence area under the curve is tau. Since the most of the area under the central peak of the transition probability is proportional to tau, so the central peak becomes narrower and higher as time increases. This is exactly the property of Dirac delta function. So this is about the explanation of this graph. At the beginning of our lecture, we have seen the transition probability between m to k is 2 pi tau divided by h cross modulus h prime km squared delta ek minus em. The transition rate is defined as transition probability per unit time. That is p m to k tau divided by tau. So tau you bring to the left hand side, then this will be defined as a transition probability per unit time. So which is equal to 2 pi over h cross the matrix element, the square of the matrix element h prime km modulus square delta ek minus em. This delta function exists only ek equal to em. So this for constant perturbation is the transition is at the same energy level. So that is delta ek minus em guarantees the conservation of energy in the time limit tau tends to infinite. The transition rate is non-vanishing only between the state of equal energy, that is Ek must be equal to Em. Hence the constant perturbation is time independent, neither removes the energy from the system nor supplies the energy to it. The energy conserving transition. This transition is energy conversion conserving one. Now we will see about the Fermi Golden Rule. The total transition rate associated with the transition from an initial state into a continuum of final state the rho of Ek, that is the density of the final stage. This is a density of state at the final energy level. That is number of states per unit energy interval. That is number of final state within the energy interval Ek and Ek plus Tek. Then the total transition Wkm is this transition you have to integrate this. This is rate of transition. Then you have to integrate with respect to rho Ek Tek. Then you know very well that this rate of transition just now we have seen is equal to this. That is 2 pi over h cross modulus h prime km square delta ek minus em. So here you take constant outside the integral. This is the constant you can take outside the integrals. Then this will become 2 pi over h cross modulus h prime km squared integral delta ek minus em rho of ek dek. This integral is non-zero only if Ek is equal to Em, because this is Dirac delta function. Only this delta is 1 only if Ek is equal to Em. So now you can replace Ek by Em. So the total transition is equal to 2 pi over h cross, then this square of this matrix element rho of Em. This relation is called Fermi Golden Rule. It says that in the case of constant perturbation at sufficiently long time, the total transition rate become constant. That is time independent. That is Fermi Golden Rule. Thank you very much for watching my video and supporting me continuously. Thank you very much.